In this section, we're going to talk about the bisection method. And the basic idea is that if there is a root of a function between two values of x, then the function will have to change sign at least once. If there's only one root, then the value of the function to the left and the value of the function to the right must be of different signs. This can be used to locate the existence of a root. As he shows here, if there are two roots between the lower x and the upper x, then they may have the function value may have the same sign. But if there's only one root between the lower x and the upper x, for instance, as in the case here, there's only one root between this value of x and this value of x. Therefore, the sign here is positive, the sign here is negative. The two have changed sign. So this description gives you an algorithm, and mathematicians should like algorithms because you should be able to take this description and take it directly and implement it on a program. In our case, it's going to be a spreadsheet. So the idea here is you choose two guesses. Your initial guesses should be such that the value of the function is different, has different sign for the two guesses. That means there must be at least one root between these two. So if we do x lower and x upper, the function must change sign here somewhere. It could go down or it could go up, but it must change sign at some point. So what you do then is, well, the question is, where is this root? Is it over to the left or is it over to the right? Where's the best guess? Well, the best guess is that it's in the center. Okay, so guess that it's in the center, and that's this point here. You estimate the root as the midpoint of those two values. Now, if you look at the midpoint here, in this case, the midpoint was here. If you look at the midpoint here, look at the function value at the midpoint and at the two endpoints. Notice here, there's a change in sign. That indicates the root's over here. Over here, there's no change in sign. The root's not here. That's what this here is. If there's a change in sign between the lower x and the midpoint, that means the root's here. If there's a change in sign between the midpoint and the upper x, that means the root is over here. So if the root's down here, you set this as your new interval and you continue to search. If the root's up here, you set this as your new interval and continue to search. This is called an iterative method because once you set the new interval, you do exactly the same procedure you did with the original interval. The nice thing about bisection method is you have an exact estimate for the size of the error. The error can't be any larger than half the width of your interval. Okay, so that tells you exactly how accurate you're going to be. Now, he uses a different method here for estimating error. I'm not going to use this method, but I'll just say here that the maximum error is equal to 1/2 times the length of the interval. And as I go through and construct this algorithm, I'll explain this again. Hopefully it will be more clear exactly what I'm doing. All right, so let's go right into the spreadsheet. And make this a little bit bigger. So let's go ahead and this is going to be the bisection method. Okay. By the way, the problem of finding roots is a very important problem. Many equations can be written as some function evaluated at some point x is equal to 0. And that's just the problem of finding roots. All right, so let's go ahead and, as our usual method, we make that bold. So let's start with our function. Okay. Now let's try a function. Suppose we try the function, again, we can do cosine. And we'll call that our function f of x because we'll be referring to f of x below. Now, when you do the bisection method, let's look at this algorithm back here. You need a lower and an upper limit. That's what you need. You have f. You need to choose two initial guesses, x lower and x upper. So let's go ahead and choose that here. This is the lower x, and this is the upper x. Okay. And let's see. We know that cosine has a root at pi over 2. Pi over root 2 is about 1.5. So we know that there's a root between 1 and 2. All right, so those will be our two values. Now, as I mentioned, this is an iterative method. That means you go through these steps multiple times. So in my first column, I'm going to put the iteration number. And that's going to tell me how many times I've gone through the procedure. Now, when I've started, I'll call that iteration 0, because that's just what I have to start with without having done any work. Okay. So let's see. During every iteration, we're going to have a lower and an upper. And we're going to change our lower and upper depending on the results of the previous test. So I'm going to start out here with XL. And I'll have here X upper. Okay. Now, during the computation, you need to take the average of these two, which is XL plus X upper divided by 2. That's going to be the midpoint, the mean of these two values. And in order to find where the which of the two intervals the root is in, I'm going to have to evaluate the function at these 3 points. So I'm going to take f of XL. I'm going to take f of X upper. And I'm going to have f of XL. Let's call it XM. Okay, so this value of XM is the same thing as this mean value that's halfway between XU and XL. So I'm going to put an XM here. And I think it may be useful for me to draw a picture as we go along so you can see what's going on. So I'm going to go ahead and draw a picture for you. All right, so what we've started out so far, our XL is here, our XU is here, our XM is here. I don't know exactly what the function looks like, but it's going to be something like, I'll draw it this way, something like this. Okay. And it's possible that if XL and XU are not chosen well, there might be multiple roots in the interval. That's up to you. Before you start the algorithm, you need to find an interval small enough that brackets the root that you're interested in. Okay, so let me go back and I'll refer back to that picture as we go along. Now, the function that we're using now is cosine between 1 and 2. So my original XL is going to be this lower limit that's given me. And my original upper limit is going to be the upper limit that's given me. So I click there on B5. This XL I could write as, well, I could write as this plus this over 2, or I could simply write it as average. of these two. F of XL. Now my function is specified as cosine, so I'm going to put here equals cosine of XL. Okay. And notice how I have this arranged over here, that I have XL, XU, XM, and FXL, F of XU, F of XM. So if I take this and I fill right, the second one will give me F of XU, the third one will give me F of XM. So I'm going to fill right, and that will give me the values of F at all of these points. Okay. Now, the point is that we need to, what we do next depends on the result. There's really two possibilities. What I've shown you is one possibility. And the other possibility is we have XL, XU, and XM. And it's possible that the function is over here. All right. Now notice that in this case, F of XL times F of XM, well, in this case, one is negative, one is positive. So the product is less than 0. In this case, both XL and XM are negative. We have F of XL times F of XM is greater than 0. In this case, our new interval should be this interval here. In this case, our new interval should be this interval here. So we have a conditional depending on the two different conditions. And the condition is we want to check whether or not this product, F of XL times F of XM, is less than 0. All right, so let's go back to our spreadsheet and see how to implement that. First of all, this is the 0th iteration. The first iteration, we have 1. Here we have, so now we want to take a conditional statement. So I'm going to have equals if, open parentheses. Here I have a logical test. Now the logical test that I want to look at, if you look back at my diagram here, the logical test I want to look at is FLXM, if it's less than 0 or not less than 0. So let's go back here. So here, my FL is here. My FM is here. Okay. If this is less than 0, what am I going to do? In that case, my new lower limit is going to be the same as my old lower limit. Okay? So if that condition holds, my new lower limit is going to be the same XL. If that condition does not hold, my new lower limit is going to be the midpoint. That's here. Okay, so I'm done with this statement. All right, now what about the lower limit? The upper limit, I'm sorry. Similarly, a conditional statement with the same condition. So if this XL, F of XL times F of XM, I think I made a mistake in the previous one. We'll have to check and see if that's correct or not. So if this product is less than 0, in that case, my lower limit is going to be, my upper limit is going to be XM. Okay? So if this condition is true, then my upper limit is going to be XM. If not, it's going to be XU. So I'll take this one. Okay, so let me check these equations here. This one here. All right, here what I'm doing is I'm taking if E8 times F8 is less than 0. All right, notice that I made a mistake here. I'm not concerned about the product of F of XL and F of XU. I'm concerned about the product of F of XL with F of XM. Therefore, this red box is mistaken. I need to go back and change that. That's not F8, it's G8. So now look at the double click here, and you can see my condition depends on the product of this one and this one, which is correct. Okay, so we can see in this, let's see if it works in this case. In this case, we have the f of xl is positive, f of xu is negative, and f of xm is positive. Which case is that? Well, if you go back here, that's in that case actually it's kind of the reverse of this one. Both of these two are positive and the other one is negative. That means that the root is in the second interval. Let's see if it worked correctly. All right, it did. For my new lower limit and my new upper limit, it chose the second half of the first interval. Okay. Now, once I'm in the second half, I can do the same thing. I'm going to divide that interval in two and repeat the process. So here what I want is the average of these two. But I already have that formula here. This one here takes the average of these two. If I fill this down, Control D will do a fill down, then this will take the average of these two. Okay. Now over here I want to take f at these three values of x, but I already have that equation here. I can simply fill this one down. Whoops, I'm going to hit escape. There's a mistake there. I can fill this one down. In fact, I can fill all three down with a Control D, and that will give me my new correct values. Lower limit, upper limit, midpoint. According to this, since the sign of this XL and f of xm are different, I should choose the lower of the two half intervals. But by this time, I really have enough formulas in there that are correct, so I can simply fill down everything. Let's take several more iterations. One way to do an iteration is each iteration number is one more than the previous. So instead of writing a 1 here, I'm going to write this as equals the previous plus 1. That way, when I fill down, it will increase by 1 each time. Okay, enter there. And then you can see that formula. Now I'm going to select this whole row across and go down. I don't know how many times, and I can do a fill down there. And let's see what we have. I think these columns are too fat. I'm going to make them a little bit thinner so I can see what's going on. Let's go here, column width. Let's take it down to 6.9. Still have plenty of digits. Okay, I need a little more space there. And let me scroll. Let me zoom in out. Oops, let me zoom out a little bit so I can see everything. All right, so what's going on here? My best estimate for the root should always be the midpoint. Okay, so here I have xm, and here I have f of xm. We can see that we're getting this value is 1.5707, 1.5707, 1.57079. This should be very close to my actual root. Okay. Now we know that the actual root is going to be pi over 2 because cosine of pi over 2 is 0. So let's go ahead and do some error investigation. Okay, so for the error investigation, I should put the actual root in. So let me put that here, actual root. The actual root is pi over 2. The way I type pi into a spreadsheet is equals pi, open parentheses, close parentheses, divided by 2. Right, so that's the correct value. Now let me go ahead and make this yellow because these are my inputs. My algorithm is here. Okay. All right, so these are my algorithm steps, so I'm going to just go ahead and make this table blue. XM actually is the same as here, so we'll just do that. By the way, if you want to center these headings, I can select these here, and I can go here to center, and that maybe looks a little bit better. I can center this one too. Go here to center. Okay, so let's see. I told you that when you do this algorithm, the maximum error is half of the interval width. Okay, so I'll do the maximum error, and then here I'll do the actual error, and we'll plot these two and see how they work out. The maximum error in this case is going to be xu minus x1 over 2. Okay. And that same formula is going to carry down, so there's no problem with that. The actual error here is going to be equal to the xm, which is the midpoint, so I'll just call this absolute value, of the midpoint minus the actual root, which is here. And I'm going to want to fix this reference, so I'm going to hit the Shift F4, and we'll close that. So take a look at this formula here. Absolute value of the difference between the midpoint, the midpoint and the actual root. All right, so notice that here we're actually a lot better than the maximum error, but we'll see how these two converge as we go down. So I'm going to go ahead and fill this, I'm sorry, I should fill down from here. Control D will fill me down. Okay, and let me put this in a different color because these are my errors. I'll make that red. Okay. All right. Now let's go ahead and plot these two. I'm going to just grab them both like this. And we'll take this chart here. In this case, I want a line chart. And we'll just do lines with points. And I think everything here is okay. Okay, and I have the names here, max error and actual error. So everything looks okay. And here's, this is going to be iteration number. And this is going to be error. And let's see what this looks like. All right, we can see these errors going down to 0. As in our previous error plot, it's more useful to do a log scale. So I'm going to click on the y-axis, right-click on the y-axis, format axis, log scale, and we can see what's going on here. The theoretical error, the maximum error, is a straight line. The actual error is kind of bumpy, but you can see that it pretty much follows the same trend. That means at each iteration, I'm having the worst possible error. Okay, so this is a good error analysis that, as I mentioned before, that's one very good thing about the bisection method, is that you know easily and pretty closely what the error of your estimate is. It's a slow method. It takes a lot of computation, but it's very dependable. Okay. So let me finish up here. I'm going to click in my spreadsheet. I guess I just want to make this smaller. Let's just compress this a little bit. Let's maybe compress too small. Let me make this bigger. And we'll uncompress this. And there we have our error analysis and our implementation of the bisection method. Okay.